So we're going to look at equivalent forms of exponential equations, and we have 4 examples here. And in all of our examples, we'll kind of keep this in mind, we want our exponent to be written as a base 2. So 2 to some power, we just don't know what it's going to be. Okay, so in this case, there's a couple ways we can go about doing this. First of all, we can try to see if we know any values of base 2 that would be equivalent to 8. Like we can actually go through our powers. So we could set it up by going, 2 to the power of 0, we know as 1, and anything to the power of 0. So we probably don't need to write that one. 2 to the power of 1 gives us 2. 2 to the power of 2 gives us 4. 2 to the power of 3 gives us 8. Works out perfect. There really is no work for that. We say 8 is equal to base 2 to the power of 3. Okay, in our next one. Very similar. We're going to focus on just the base, and we're not going to worry about this power yet. So base 4, we know that we can do 2 to the power of 2 to replace our base 4. So what we'll do here is we'll replace 4 with 2 to the power of 2. And because it had a previous exponent, we're going to multiply the new exponent by the old exponent. Okay, so that's 2 by 3. This gives us 2 to the power of 6. If we were to equate both of these, we should end up at the same answer. We can try to prove it here. 4 to the power of 3 gives us 64, and 2 to the power of 6 gives us 64. So perfect, they're equivalent. Let's get rid of those signs for your notes. Okay, next one here, we have a radical. So when there's no value written here, it's on the assumption that it's the second root of something. Okay? And we can represent any root function by turning it into a fraction. So we'll have 16, and it'll be 1 over whatever the root is. So 1 over, and in this case we have root 2, so 1 over 2. In our second one, we'll put this in brackets. In our second one, same idea, we have 32 to the power of 1 over 3. And then it still times our power of 3. We want to make this base 2. So we have a couple options.
After, like
the multiplication?
No, taking the root out after, like make it a base of 2 and then take the root out.
Yeah, we can. We can definitely do that. We can turn this all into a base of 2 first if you want. Maybe we'll do that on the side. So we'll show it doing 2 different ways. We'll continue with what we're doing, and then we'll do it again over here. So from here, I'm going to actually, since I know that when I multiply these two to make things simpler, that's just going to be a value of 1. I'm going to simplify my exponents. Essentially, these have to be multiplied. Same with the idea we'd used above, where we have a power of a power, so we multiply the 2. So when we multiply those two, they become 32 to the power of 1, right? So 32 to the power of 1 works out really nice. I go back up to my values. Let me see if I can get any more. So I'll continue my list. 2 to the power of 4 gives us 16. 2 to the power of 5 gives us 32. Excellent. So I know I can replace some values. 16 can be replaced with 2 to the power of 4, and that will still be multiplied by our half. And over here, I've already multiplied these out, so it's essentially the idea of just the power of 1. 32 can be written as base 2 to the power of 5. Okay, these still have to be multiplied by each other. Okay. I'm going to multiply this exponent. Yeah, so this will become 2. So we get 2 base 2 to the 5. Now, because we're multiplying the bases, or essentially the entire exponent, not just the powers, we actually just add the exponents in this case.
2 to the 7.
Yes, exactly. So 2 to the 7. So, like you said over here, what if we decided to turn them into their bases first? I'll just put these in brackets. We don't need this x sign here. We have root 3. We can really cancel those out right off the beginning if we notice. Okay. 16. We know 16 can be written as 2 to the 4th. So we have the second root of 2 to the 4th times third root of 32, which is 2 to the 5th. And the 3 here. Right away, I'm going to just acknowledge that these two cancel each other out. So we have 2 to the 5th. And in this case here, same idea. We're going to write it as an exponent again. So we have 2 to the 4 times a half multiplied by 2 to the 5th. And we already know from below we are going to get 2 to the power of 7. Either order, it doesn't really matter.
I like that one better.
Okay, then use that one. Okay, and D. If we go ahead and look up here, we don't really have. We're looking for a value of 12, so we know it would fall somewhere between exponent 3 and exponent 4, but we don't know exactly where it would fall. So we need this to become a base 2. So what we're going to do here is I'm going to set it equal to base 2, and we're going to give the exponent, the unknown, a variable. We can call it x if we like. We could call it k, whatever you really want. So now we have 12 to, technically, like the power of 1 is equal to 2 to the power of x. So we're going to use our, we learned in the last chapter, we're going to use log base 10. So I'm going to find log base 10 of 12, and we know the power comes down times 1. There's really no need for that, right? So let's just kind of, we know that's not going to change anything. Okay. On our other side, though, this power that comes down will be multiplied by x, and we'll have our log base 10 of 2. Okay. So now what we have is we can bring this over, and we're going to get x is equal to log 12 over log 2. It'll give us some decimal value. Do you know what it is? Did you check?
3.58 approximately.
Approximately. But let's say they want us to be very, very exact. What we can do is write this as a base. We can say 2 to the power of log 12 over log 2. And that is a very, very exact answer for 12. If you want the approximation, and it depends what your teacher wants, we can say 2 to the power of 3.58 is approximately 12. But this one is precise, where this one is approximation, right? And there's some equivalent forms.